But welcome to Module 4, Virginia Earth Systems Science Scholars. This presentation is meant as an addendum to the materials you already have in your reference section, so please check those, read over those carefully because we're not going to be able to go over every single detail in those. But here we're going to talk about the composition of the atmosphere, its layering, and then some of the issues regarding energy flux and pollutants. So you may already know from earlier coursework that the atmosphere, the Earth's atmosphere is layered. And so, of course, the troposphere is the lower portion of the atmosphere where most of the weather occurs and where we live, which extends from the ground level to, well, it depends on where you are in terms of latitude, the time of year, and so forth, but generally above around, up to and close to 30,000 feet or so. And at which point you get to the tropopause, where temperature has been decreasing through the troposphere, and now it begins to increase as you enter the stratosphere. The key feature of the stratosphere for most of us is the existence of the ozone layer there, which blocks most of the ultraviolet radiation, especially that bit of radiation here that we're very concerned about. Some shortwave radiation between UV and visible, of course, makes it to the Earth's surface, and that's part of what warms the surface to eventually release infrared or long-wave radiation back into the atmosphere to help warm us. But in the stratosphere, at least, temperatures begin to go back up, and then eventually reaching the stratopause, where we then move into the mesosphere, and in the mesosphere things begin to go back down again, and then eventually in terms of temperature and until we hit the thermosphere. So this is the layering of the atmosphere. There's some other features, of course. If you're going to do some observing either of the atmosphere or of space, of course researchers with NASA and other places need to be cognizant of the absorption and reflection or scattering of various forms of electromagnetic radiation from the sun. So if you're an X-ray astronomer, you'll probably do most of your observations from above the atmosphere with an X-ray sensitive telescope, because X-rays don't generally penetrate far enough into the Earth's atmosphere to be able to observe. Likewise, when you're designing sensors to look back on the Earth, you design your sensors to pick up the signals you want, and you're using various frequency bands to do that, and you're cognizant of where these frequency bands are able to penetrate, to be able to pick up information. So, so one other thing to point out here, and we'll come back to this later, the troposphere is not a uniform, homogeneous layer. It actually has some layering in and of itself. We'll come back to that in a minute because it's very important. You may also be familiar with the percentages of gas, or at least roughly what's in our atmosphere. Most of our atmosphere, contrary to some popular belief, is actually nitrogen and not oxygen. Though oxygen is a significant portion, and going back to the beginning of life and the evolution of photosynthesis has been since then. The early atmosphere on the Earth didn't have nearly the concentration of oxygen we have today. So oxygen's a byproduct of biological activity, which is a good thing because then we are able to breathe. So it's a product of respiration. Ozone in the stratosphere is an important thing, and so it's good to have that there. Ozone in the troposphere is not, and so it's light blue here. Everything that's light blue is actually an anthropogenic pollutant in some form or another that causes problems, whether it's an aerosol, direct greenhouse gas, or what have you. So the other gases in the troposphere and stratosphere include, of course, oxygen and water vapor. Water vapor is more of an issue in the tropopause, or below the tropopause, because that's, of course, clouds and the interactions between trees transpiring and bodies of water and so forth that are, of course, located and interacting with the atmosphere in the troposphere. And there's some other trace gases. Argon, CO2 is a major greenhouse gas, but it's also a trace gas in terms of its actual concentration in the atmosphere, in the troposphere. It's not nearly as much of that as there is as O2. But of course, the anthropogenic or human contribution to CO2 is significant over the last couple hundred years. We'll come back to that in a moment as we talk about climate. Before we talk about CO2 directly, it's important just to talk about how the Earth's surface is as warm as it is, and that's just primarily because the sun is, of course, emitting its electromagnetic radiation. Some of that is shortwave, just very close to the visible portion of the spectrum, and it penetrates and eventually is absorbed by the Earth's surface, which could be the ocean and the land, and then is re-radiated as long-wave radiation, which is then trapped by the greenhouse effect and the greenhouse gases in the atmosphere, which include CO2, but also include methane, water vapor, and then various oxides of nitrogen. So those are the important greenhouse gases. There's also aerosols, and these aerosols include things like volcanic ash and sulfates, as well as wind-blown particles of dust and sediment. Then, of course, there's clouds. Clouds and ice are both very light-colored, and so they tend to have high albedo and reflect the sun's radiation directly back out into space. And the more clouds and ice you have, the cooler the planet generally is going to be. But if you melt the ice, then, of course, water is much darker in color, and ocean water tends to absorb that radiation, which becomes a positive feedback to the climate system as a whole. There's also, of course, now going with the anthropogenic part of all of this, there are, of course, greenhouse gases we emit, CO2 and methane, and, of course, the oxides of nitrogen, and of course, various aerosols like black carbon that are very, very significant absorbers of radiation because of their color and composition. There are other, of course, aerosols that we release through power plants and so forth, such as sulfates, which have a net cooling effect. But the black carbon has a much more significant effect in terms of its actual changes to the climate. So these are things that force the climate, that force it to be warm, and even force it to be cool, that directly affect the climate. There are other things that feed back to the climate as you're doing those, as you're forcing the climate in various ways. There are other things that happen that provide positive feedbacks, which amplify the warming, or negative feedbacks which take away from it. And of course, water vapor, being a greenhouse gas, is going to be a positive feedback. The emissions of CO2 and methane from melting permafrost is a positive feedback. Negative feedbacks include ice albedo from snow, or albedo, a reflection from snow and ice, and of course clouds. The ocean is an important sink for carbon, and is always exchanging with the atmosphere. And in fact, the CO2 we emit oftentimes primarily goes into the ocean first, and then eventually the ocean can only hold so much until it's saturated with CO2, and then it becomes an issue of mostly exchanging with the atmosphere. And when that happens, of course, that could be what we refer to as a positive feedback, but perhaps also an example of a tipping point. But there are other more prescient tipping points. And tipping points are places where you've got to force the climate to be warmer, and you've got positive feedbacks working now to amplify that effect, and then you reach a place where, in various systems around the planet, permafrost being one, and so forth, where major changes occur that then move the whole system along even further and much faster. And then so like running up a hill and then running back slowly and working hard to go up that hill, and then you get to the top and then you run back down the other side because you can, and it exacerbates what's already been happening. So these are tipping points, and there's some examples of these around the planet here. Okay, now let's go away from climate a little bit and talk about some of the other important gases and particles that compose the lower two layers of the atmosphere primarily. Aerosols, ozone, and other sometimes what we call pollutants. And let's start with the stratosphere and work our way down. So the stratosphere, of course, is important to us because within the stratosphere is ozone, and ozone is constantly being produced and destroyed in the stratosphere, and generally is in a pretty much a dynamic equilibrium with the natural system. And so ozone is being produced by the combination of free oxygen with O2 particles to create O3, which is the ozone. And then it's also being destroyed through other chemical means. And one of those chemical means, especially some 2 decades ago, was primarily through aerosols that were emitted by propellants and refrigerants from these were industrially produced chemicals that were emitted into the atmosphere. Hairspray was one that it often comes up as that, freons and things of that nature. And the presence of those in the stratosphere unbalanced the equilibrium and eventually led to a thinning and even a hole in the ozone layer. And now this is an example where people around the world did manage to come together and signed the Montreal Protocol, which then banned certain chemicals over a period of time. And then when those chemicals began to come out of circulation, we began to see big changes and improvements in the ozone concentrations in the stratosphere. So that is very important because ozone blocks ultraviolet radiation, which is quite deadly to the biosphere. So naturally, the stratosphere is very important to us. Making sure that we have a robust ozone layer there is important. There are other things that go up into the stratosphere, of course, that are aerosols that come from the troposphere, not just CFCs, but also natural things like sulfates from volcanic eruptions and so forth. So these are all very important things. Circulation within the stratosphere tends to be, in terms of the air circulation, tends to be on longer time scales as well. So it's important to point that out. Okay, now below the stratosphere, of course, is the troposphere. And there is, of course, gas exchange between the troposphere and the stratosphere, as evidenced here by this the water vapor traversing the tropopause and this destruction of O3 or ozone by halocarbons or CFCs. But most of the emissions and so forth produced by humans and natural sources stays in the troposphere. And a lot of it just interacts down here below the planetary boundary layer, which is that other part of the troposphere I alluded to earlier. So this is where not only is air encountering the land and creates a friction, but you get changes in the convection within the atmosphere in this part of the atmosphere, because you got the warming and the cooling of the land that happens very unevenly, and the water that happens very unevenly, and so forth. You can end up with a diurnal effect, which I'll point out in a moment. But just to illustrate, one of the things here with this is that some of these things occur on very short time scales because they're very close to the ground. The travels of these various aerosols and so forth, and some of these occur on much longer time scales. I mean, for instance, the residence time for CO2 that makes it up into the free atmosphere portion of the troposphere tends to be anywhere from, I've heard estimates from 700 to 10,000 years, depending on where it is in the troposphere, in this portion of it. So again, circulation at these higher altitudes takes longer. Now, of course, the stratosphere, the troposphere, is very important for aviation, and it's very important to be able to understand the stratification within the troposphere. So this is a big thing that NASA studies through some of its Earth observing missions, like Calypso, which is looking at the cross section of the atmosphere and looking at aerosol plumes from volcanoes and so forth, but also being able to provide information to the FAA regarding, or the FAA can use that data to help pilots navigate safely through this portion of the atmosphere. So the planetary boundary layer is the lowest troposphere, and it varies. Of course, its elevation varies based on topography, based on the time of year, seasonally, and of course based on latitude. But overall, the general picture of what goes on below the planetary boundary layer from day to day is pretty consistent. So at lowest levels, during night you'll have a stable boundary layer. Cool air is denser and tends to lie below warmer air, and then the residual layer on top of that will be a little warmer. But of course, with sunrise begins to warm up the ground, and that long wave radiation gets radiated, and we end up with a mixed layer. And so the atmosphere becomes very mixed during the day, and these boundaries are oftentimes where you have a lot of the very unstable weather that you have during the day. Now, there are many, many other variables that affect weather. This is just the general picture. But above this layer, in the free atmosphere portion of the troposphere, it's not nearly as busy as it is down here because of this uneven warming of the surface and these inversions that can happen. And these inversions can affect, these temperature inversions can affect the distribution of aerosols significantly and lead to these times like in places like Beijing and Rochester, as in your text, LA and Athens, Greece, and places that have really big problems with smog. So, and then of course, ozone is also produced at ground level through anthropogenic means, and it's a very complex chain of reactions. But generally, it's photochemical. The sunlight is the catalyst, but it's a combination of the nitrous oxides, the VOCs. And then of course the production of ozone. Ozone is not a good thing to breathe in. It's a bigger molecule than O2 and is detrimental to your lungs. You can see here, because of this reaction, you can see this inverse relationship between the nitrates here and the ozone. Because when nitrates are low, then the ozone's being produced, and you can see that's right during the middle of the day. So this is photochemical ozone being produced, which is a component of smog, especially in urban areas, especially in the lower altitude urban areas, or in rural areas. I mean, a lot of this ozone gets blown from power plants out into rural areas, and actually significantly affects rural air quality as well. So, and of course, it's detrimental to both human health and plant health. So the entire biosphere is affected by this in negative ways. Here's some examples, of course, of how weather interacts with ozone. So again, the lower troposphere below the boundary layer is quite complicated. And here you can see, let's just look for a moment, the difference between the diurnal patterns between these two locations. So at Big Meadows, which is a major ozone monitoring station, or a major monitoring station, is located in Shenandoah National Park. Beautiful place, by the way. If you ever get a chance to go to Big Meadows, it's great to walk around the meadow. But there's not a lot of variation in the ozone levels. There is, of course, on a broader scale, but not necessarily daily. And it's because it's higher up in the atmosphere and you're closer to the boundary layer. So there's not as much going on there. As opposed to Richmond, which is much lower in altitude. And you can see that daily, and of course it's an urban area with a lot more cars. And so the ozone is being produced right there on site. You'll notice that the overall trend daily may be up and down, but there is also an overall trend that is dependent upon weather patterns. And so this particular spread of time in the summer of 2013, there were some fronts moving through, and they actually depressed the ozone levels. And so even both in Shenandoah National Park and in Richmond, so at the same time. So while the daily pattern, of course, is very different at different altitudes, and because of the production of the presence of cars and things of that nature, weather, rain and low pressure systems moving through can actually improve air quality. All right, so of course NASA's studying these things, and they have systems that are looking at aerosol optical thickness and things of that nature. They have a whole fleet of Earth observing satellites focused on the atmosphere, and those are discussed in more detail in the reference materials. And please do go look at that, of course. Natural aerosols, as you see in this image here, some of these aerosols that are in these really thick areas are human-induced primarily. Others are natural aerosols. Now, there's not necessarily volcanic eruptions going on during this particular time, but you can see here that there's a color coding here. Yellow areas are predominantly coarse particles like dust, and red areas are mainly fine aerosols like smoke or pollution. So the yellow areas, you can see right over here by the Sahara, and so this is an example of a natural aerosol coming off of the Sahara Desert, and over here in the Middle East. These red areas are primarily pollutants, and over here it's likely forest fires out of the Congo. Here through South America, it may be more of that, but it's largely in North America, and in this area over here is largely, and it could be industrial pollution and so forth. But these aerosols are a variety of things. It's not just a uniform bunch of stuff. Some of it is dust and ash and gases and sulfates and things of that nature. Others are actual black carbon, and then, of course, human-produced sulfates. So there's a whole mixture of things. You can pick them out based on their composition and the way they reflect electromagnetic radiation. But the big one for climate is really, and human health, and not just human health, but the biosphere health, is really black carbon. Black carbon can attach itself to sulfate molecules, and sulfate molecules have a net cooling effect generally on the climate, but black carbon, because of its composition and its color, has a much more intense warming effect on the climate. And so it's likely that as much warming is occurring as much global warming is occurring due to aerosols, black carbon, as there is from CO2 emissions. So again, sulfates and nitrates tend to have a scattering effect and cooling effect, and they also, of course, play a significant role in the condensation of water to form clouds, whereas aerosols like black carbon have a net warming effect, and it's a very significant one at that. So, of course, in terms of plants and human health, aerosols can get in the way of photosynthesis. And that's because their particles are so small, they can move in and out of the pores of plants and becomes a problem. Likewise, they move in and out of the pores of the alveoli in your lungs and so forth, and can cause problems because your bloodstream can't absorb the ozone and so forth. So it's children and the elderly are most affected by these things. And so from a human health perspective, it's an asthma issue, it's breathing difficulties, cardiovascular issues, and so forth. Not good. So this ozone at ground level is something that can be prevented, but in order to prevent it, you have to find ways to prevent the volatile organic compounds and nitrates and things out of vehicle exhaust and industrial exhaust from being put in there in the first place. So it's a byproduct of industrial society. Some of these, of course, these aerosols have different sizes, and you have 2.5 micron sizes, and then 10 micron sizes, and these include dust, pollen, molds, and so forth. A lot of these are natural pollutants or aerosols, and then you have these results of combustion, the 2.5 micron pieces. This is just showing you to a human hair how big these pieces are relative to one another. All right, and that concludes our presentation for Module 4. Good luck and enjoy.